Alrighty then, hello and welcome again with Graphust. I hope you're not sick of the topic yet, because we've got at least 2 more videos coming. Remember the last time we talked about Graphust, it was really tackling the whole idea of handcrafted logic, which was cumbersome to say the least, or I would even call it irritating to, let's stay at irritating. First, let me just show you how it works now. So let's go with a triangle. We go from A to B, then from B to C, and from C to A. Then let's go with the example that I was most proud of in my previous version, which was the multi-line, which goes from A to B, B to C, C to D, but also B to E and from E to F. We've got also the possibility to converge the items, so from A we go to B and D, and from both of those we're just getting back into C. And then lastly, when we want to go from A into 4 different directions, well, it sort of looks like a fan. Alright, this is all fine and dandy, but what happened? Well, what happened is I actually decided to use the algorithm that was done by somebody smarter than me, which is called the Eades algorithm. Believe it or not, it actually originates from 1984, and I found the algorithm to be explained very nicely with examples by Philipp Kindermann. You'll see a link to his channel in here somewhere. Huge shout out to Philipp. Thank you, mate. Now, how does it work? It gets your graph and it's tried to plot it out with an algorithm that is a force-directed algorithm. As I mentioned, we're talking about the Eades version of the algorithm, but there's actually quite a few of those. And the easiest way to explain it and to imagine it is to take a look at this example again, and now imagine each of the nodes is actually a magnet, and the magnets are the same polarity, so they actually push away from each other. Also, each of the arrow is a spring, so the spring brings in the tension between those magnets. So now the whole idea is that you usually have more magnets than springs. So for example, if we take a look at A, it is actually connected as a spring to B and to D, but is getting repelled by B, D and also C. If you treat the nodes and arrows this way, you actually can imagine how they move and how they operate in this sort of physical system. Now let's take a look at the implementation. Well, you actually start with a random placement of all the nodes, and what I did is pretty much just plot them maximum 3 in a line and then just 1 after each other. So when we are talking about 5 nodes, they will be actually placed sort of like this. There will be A, then B, then C, and then D, it just loops around, and then E. So this is the placement I went with. You can easily go with absolutely random, that's also fine. I sort of like this. So once we have the initial position, what do we have next? We actually go into the algorithm. You can either stop the algorithm after some number of iterations, and this is exactly what I did. I just ran the algorithm 100 times and that's about it. You can also finish the algorithm when you reach the equilibrium that you want, right? For example, you can reach the lengths of the connections between the nodes that are similar to each other. You can also stop when the forces that you need to apply to the nodes are just very small, like smaller than some epsilon that you anticipate. For the simplicity of it, I just went with 100 iterations, that's it. Now, how does the iteration look like? There's actually 2 loops in here that are important. So first one calculates the forces that work on each of the nodes. The second loop actually goes through the nodes and apply those forces. It's important that we separate those two steps, because when we start calculating the forces and move it right away, then actually that influences the next calculation of the next forces and so on. So it's important to separate those two loops. In the first loop, we've got another two loops which are calculating the forces of attraction and also apply forces of repulsion, which is calculated for all other nodes. Once again, think magnets, right? In terms of how to calculate the forces of attraction and repulsion, that's actually the part of the algorithm, so I didn't think that through, right? But it's based mostly on the Euclidean distance. So for both of those, actually, there's two main things that are important. First is really how the force is directed, and this is important because if we are talking about the force of attraction, then when we are looking at point A or node A and comparing it to node B, then the force will be directed towards node B. The force will be applied actually the exact opposite way when we are talking about repulsion. So both are based on the distance but have opposite vectors. And yes, as you can imagine, for each of the nodes which is connected to our current node, there's actually both forces working at the same time. It's only the different force magnitude that is applied in here. So this is how we calculate the force magnitude for attraction, but this is how we calculate it for repulsion. And those forces get combined, so in the end, for each of the nodes, there's actually one vector of force applied to it. I've also caught a weird thing in here. Due to the way I'm placing the nodes, there's actually a possibility when you do a triangle to fail. So let me show it to you. This is something that I've added, right? So when we go now with the triangle, as you can see, it stays in the line. It just doesn't really move that B out of the line, which it should do, right? So what I did is when the forces are 0, I've actually added a fake force in here. So you actually move that B out of the line and then calculate again in the next iteration, right? So when you apply that fake force and fake move, you now get a proper triangle. Once again, thinking about nodes only, not the arrows, right? This is a triangle. So what I do for the arrows is just start with the points, or rather the anchors of the nodes themselves, and then judging by those anchors, I decide which side of the node I'm taking. And those two functions that you see right now on the screen pretty much cover that not only do I actually attach to the side of the node, but also I attach in different places. So when we go this, and for B, as you can see, we're using the bottom anchor twice, we are actually targeting different points. Alright, with that out of the way, let's take a look at the bad side of things right now. So my biggest gripe with this logic is that it can be suboptimal, to say the least. If we take a look at this graph, in the previous version it actually looked sort of like this. That was a little bit more optimal and better usage of space. It's still easy to read, which is the most important one, right? The other thing is the logic behind the arrows. Because this thing, as you can see right now, and then going to the middle point, should or could be much easier. So maybe I need to look for another old algorithm that is trusted and true, perhaps. And to end the topic, is the logic flawless? Absolutely not. It's full of holes like your Swiss cheese. Yeah, that's stupid joke, but I'm going with it. Alright. This example is actually okay. I'm fine with it. But there are ones where the arrows can get a little bit tangled, exactly like this one. If you know what you are looking at, you can still read it, but it certainly could be much easier to read, much better. Yeah, the logic is not flawless, we can certainly still improve that. Maybe that's the next step. Thank you very much guys for listening, and as always, I'm very happy you've been here. You're an awesome human being, and please consider hitting the like button. It will help me quite a ton. And as always, we can do better as a pack. Bye. Oh shit. Okay, didn't want to do that. Alright, back again. Alright, so we go node by node and we calculate for all the edges, or rather for all the connections we've I've heard there was a secret chord that David played and it pleased the Lord. But you don't really care for music, do you? Well, do you?